afterwards, he moved to Los Alamos as a postdoc, where he is now staff and leads one of the groups in the Information Science Division. So, welcome.
Thank you very much. Can everyone hear me all right? Perfect, thank you. First of all, I want to thank Mikael and the rest of his team for organizing this and for inviting me. I've been having a great couple of days here chatting with everyone. So just to get a feel of what people are expecting from this talk, let's get just by show of hands, who knows what quantum computing is? Okay, that's about 80%. Who knows what quantum machine learning is? Okay, now we're down to like 30. Perfect. So the goal of this talk, and let me do this disclaimer to begin with, is it's going to be maybe a slightly different talk from the topics of quantum machine learning, because instead of showing you all the cool stuff that you can do with quantum machine learning, I'm going to tell you about all the ways in which quantum machine learning doesn't work. So this talk is going to be about trying to convince you that quantum machine learning, there's a lot of hype out there. It's a buzzword that combines, quantum and machine learning. How can it not be good? You have quantum, you have machine learning, now you have quantum machine learning, right? But the whole point is that this is a technology that hasn't worked as well as we would have hoped, and one of the goals that we're trying to work on is how to fix this, how to do some proper quantum machine learning. So to give you a bit of an outline of the talk, the first thing that I'm going to try to do, just for the general audience, is do a brief recap of the history of quantum machine learning, just to see what are the different approaches, how we've attempted to define what quantum machine learning is, and what are the types of problems that we can solve with this technology. Then, for people who have not studied classical learning theory and who don't know what Gaussian processes are, I'm going to try to define them, especially how we can use the concept of Gaussian processes to solve learning tasks, in particular regression tasks. And finally, how we can define what we call quantum Gaussian processes and try to motivate why we think this is a way forward. And then just going to give some outlook and discussions. So let's start with quantum machine learning. The first thing that you should know is that there's going to be a lot of memes in this talk, so hope everyone is happy with that. So to begin, let's talk about quantum computing for those who don't know what quantum computers are. So one of the first questions that we can ask is, there's this emerging technologies where we can use the principles of quantum mechanics to manipulate individual quantum systems, and this enables the idea of processing information with those devices. And one of the first questions that we can ask is, what are those devices good for? Let's say that I've put a lot of money into developing technologies for quantum control. Can I actually use them for something useful? And the answer is that yes. One of the first tasks that we can try to solve with quantum computers is the simulation of quantum systems. If anyone here has worked on quantum chemistry or condensed matter, the sizes and the compute power that you need to be able to manipulate those systems and try to get answers of how a system would behave is very expensive. And they grow exponentially with the number of particles, say like fermions or light sites on a lattice for a condensed matter system that you have. So one of the first things that we want to use quantum computers for is simulate quantum systems. And here we can expect an exponential advantage, that the number of resources that we need in a quantum computer to solve a simulation task should be exponentially smaller than those needed by classical computers, of course, assuming that BQP is not in P. Then, we can start thinking about maybe more problems that are related to learning or at least data analysis. Like Grover's algorithm is an algorithm that is useful for search problems. You have an unstructured database, you're trying to find some element. Here you can expect some modest square root advantage. So this is going along the right direction of using quantum computers for data. Then, of course, the archetypal example is we can use quantum computers to factor large numbers using Shor's algorithm. And of course, this is something that we know has a lot of applications for cryptography, and we can expect some nice speedups, but of course we don't know, because we don't know what's the limits of classical computers for factoring, right? And these are some indications that quantum computers can do very useful things, and hence all the money that we're investing in developing them is not wasted money. Then, of course, we can ask the same question: what are the types of problems that we can solve with classical machine learning? And here, I don't think I have to tell anyone, there's so many things that we can solve with classical ML and artificial intelligence. And this idea of training an algorithm to solve a problem that I don't know how to solve based on data is an extremely powerful idea. And it has revolutionized how we do science, how, We talk to computers. I'm pretty sure here everyone uses ChatGPT one way or another, or has played with like diffusion models to generate like cool images, like the one that I've generated there with DALL-E. And of course, as I was saying, it's completely inevitable that if you have these two fields, we're going to ask the question, can we somehow combine them? Can we take quantum computers and combine them with classical machine learning, or vice versa? Can we take classical machine learning and slap them into quantum computers, and we call this quantum machine learning? You know, two buzzwords. This is how you get funding when you're writing proposals. So let's do a little bit of a history of quantum machine learning. The first thing that we need to know is that quantum machine learning is by no means a new field. The idea of the quantum perceptron was first introduced in 1993 by Lewonstein, and then the generalization of how do classical machines learn was developed with this PAG formalism. The quantum version of PAG formalism was developed in 1995. And after this, the original ideas for artificial quantum neural networks were proposed in the mid-90s. So we've been thinking about how to combine classical AI with quantum computers for a while. And at least these were sort of like different sparse ideas. But I think the big boom for quantum machine learning came around the middle of 2010. Here, people were using some primitives, and they found algorithms like quantum principal component analysis. If you've ever analyzed data and you've done principal component analysis, you know that this is an extremely useful tool to get what are the characteristic and defining properties of a data set. And this is a problem that we can also put inside of a quantum computer. Then, you go into Netflix or on YouTube, and it's telling you this is a video that you should watch. There's a new movie that you might like. Those are recommendation systems. People found that we can do quantum recommendation systems. And not only we could solve those tasks, they were provably exponentially better than any classical algorithm that you might have. So at that point, so this was extremely good, and people were extremely excited about this, because this wasn't just like simulating a quantum system that maybe academia works. This is something that is useful on day-to-day. And again, I think that the main principle of what we were doing here is that we were taking the basic primitives. You take a quantum computing textbook, and you're going to find some basic primitives as QRAM, the HHL algorithm, SQ-access, and we were using those for data analysis, right? And this was the golden times of quantum machine learning. We had quantum algorithms that could do things exponentially better than the best classical algorithms that we had. But then, of course, if it's too good to be true, it probably is. And then we have to talk about the dequantization results by the seminal works of Ewing Tang. And this was an incredible time, because what happened is that the initial hope of using those algorithms that had provable exponential advantages, they were all dequantized by a series of works. I don't know if you can see this down here. This is actually taken from the archive of Twitter. This is a tweet on November 13, 2018. And here, Ewing Tang found a classical algorithm that does the same as quantum recommendation systems with a comparable speed up. And this was put, I don't know if you know how to read archive identifiers. This was 1807, so this was 2018, July. Then there was quantum PCA. This was 1811, so that was November. And then you had 1811, also low-rank HHL. So in the span of just 4 months, all of the hopes of quantum machine learning were destroyed one after the other. And what she did was she just found classical algorithms that can solve those problems comparatively fast. And what was really cool is that those algorithms are based on the quantum algorithm. So she borrowed inspiration from the quantum to create classical algorithms. And just like that, almost all of those exponential speedups that we had were completely gone. Of course, there's a few that you remain, and someone might come and say, oh, but there's this paper. Sure, but those separations are not for tasks that we would consider practical, like recommendation systems or solving linear systems of equations or quantum PCA. So, this, I think, explains it very well. Ewing Tang destroying the hopes and dreams of QMLers everywhere. So the question is, why are we still talking about quantum machine learning? What happened? Why was this field still alive? So the next thing that happened was this thing that was called variational algorithms. And the key idea of variational algorithms is to try to emulate what classical neural networks are doing. In a classical neural network, you take data, you send it through some linear algebra process that you're manipulating your data, and those manipulations hopefully manipulate your data in such a way that the desired outcome is done. So this is the basic idea of variational quantum algorithms. Again, I'm not going to explain them in detail because you probably know where this is going to go. And again, variational algorithms are also not new. They were picked up in 2018, but the original ideas were developed much earlier. People were proposing variational algorithms to solve quantum optimization problems as early as 2014. You can try to find the ground states of some Hamiltonian and solve problems in quantum chemistry or condensed matter using this algorithm called the variational quantum eigensolver. This is a 2013 paper. But for some reason, those methods were just somehow lost in time. People were not really working in this technology. So what I personally think that happened was that in 2018, there was this vacuum that was created by the dequantization of most quantum machine learning results. And this vacuum was filled by variational quantum algorithms, people trying to find a new way of doing quantum machine learning. And this was also fueled by the fact that this was around the time where quantum computers started coming alive on the cloud. And this technology is kind of well amended and well suited for near-term quantum computers. So the only detail that I'm going to give about variational quantum algorithms is just a high-level overview of how they work. So the main idea is you have a problem that you're trying to solve. You're going to have some training data, for instance. And then what you're going to do is that you're going to take that data, you're going to put it inside of a quantum computer, and you're going to make it evolve through a quantum circuit that is parametrized. So for people that know quantum mechanics, quantum systems evolve under unitaries. And for instance, I can tune how long a quantum system evolves just by a time parameter, right? I turn on an interaction, I let it evolve for 1 second or 2 seconds, that's going to do something differently. Now I just use t as a trainable parameter. So I take my quantum system and I start evolving this with those trainable parameters t, and I can try to tune them and try to solve a problem. Maybe the output of the evolution is the solution to the problem that I'm trying to solve. So this, in a way, emulates how classical machine learning is working. You're just like fine-tuning some knobs in your quantum evolution, sort of like evolution times. At the end of the circuit, I'm going to make some measurements. I'm going to quantify, I'm going to measure and define a cost function that tells me how well I'm solving the task. And then I'm just going to use a classical optimizer that is going to tell me, oh, for the next time, change your evolution time from 1 second to 1.2 seconds. And of course, seconds is a ridiculous unit to use in quantum computers. You know, this is way beyond past coherence time, but it's just to give you a rough idea. And quantum machine learning with variational algorithms just became extremely popular. There was like a boom. And I think that the reason why is that this technology, first, is very simple to use. If you understood what I just told you and you know Python and linear algebra, you can go and you can do variational algorithms. And you can take pretty much any problem that you can ever think of in classical simulation, quantum chemistry, you can solve linear systems of equations, you can do factoring, principal component analysis, solve combinatorial optimization problems, generative modeling. You know, everything can be put in this very simple formalism, and it's very easy to just get going. So over the past few years, we've just seen this boom of variational algorithm papers and variational quantum machine learning, where it's just exploding. And the growth has been truly amazing and staggering. And I see this curve right here as a consequence of two facts. The first is, again, the hype of quantum and the rise of AI, and the idea that this has no provable guarantees. You don't know if this is going to work or not. All that you can do is just run the circuit, try to tune the knobs, and hope that it works. And you know, if it doesn't have provable guarantees, it's not a bad thing. Classical machine learning does not have any provable guarantees. Trying to train a fully connected neural network is NP hard, yet we can do all the things that we're doing. So, you know, why not? Just try it, see if it works. And I think that the other reason why this curve looks like this is because this has a relatively easy learning curve. As I said, I think it's very easy to pick up variational quantum algorithms. So with this in mind, we can ask the question, okay, what do we have to show for quantum machine learning? You know, we've been working on this field for over 30 years now. And the thing is that if we want to show that with this variational pipeline, there are some problems that a quantum computer can solve and that a classical computer cannot solve, we can absolutely do this. For instance, this is one of the papers, but I can point you to others, where we can find and construct some contrived learning algorithm where there's going to be a quantum algorithm that solves a task exponentially faster than any classical algorithm. Of course, the problem is that most of these sort of like provable separations, they're built for very synthetic data sets. And at the end of the day, all that they're doing is that they're encoding some cryptographic assumption, or for instance, a discrete logarithm problem, and they're just using Shor's algorithm for factorization at the end of the day. So all of these algorithms, sure, we can prove a separation. Maybe this is good, but this is not useful for anything in practice. We cannot use this to try to solve an actual problem that is going to be relevant for industry or even academia. So is this good enough? Should we be happy with this? Is this what we need to do? And of course, the problem is that if we want to go to practical stuff, as we have said, the only thing that we have left is heuristics. We can just take our models and run them and try to see what's happening. And of course, the problem here is that when I started in the field, I was doing variational algorithm. I was training my variational circuit on 4 qubits. It works. 10 qubits, it really works. Then we go to 15, it works kind of okay. You go to 20 qubits, your performance starts to really go down. And you start asking the question, what's happening here? There's clearly something that is preventing me from just like scaling up my algorithm. And what we started doing was trying to answer theoretical questions. What can we say about these heuristics algorithms? Can we prove results that are going to be average case hardness or worst case performance? And what we saw is that, just like classical machine learning, as we said, we don't have provable guarantees. But while we can achieve success for small problem sizes, and we don't have promising heuristics. And we cannot test these algorithms at scale just because we don't have large-scale quantum computers. I can only do whatever I can do in my classical computer. And of course, the problem is that we've managed to prove that there's a lot of issues like vanishing gradients that are going to appear, or a very large number of local minima. And there's some very fundamental differences between classical and quantum machine learning, where you might say, okay, you have vanishing gradients. Why don't you use the techniques that have been used in classical machine learning to get rid of them? And the problem is that the way in which we process data in a quantum computer is fundamentally different by how we process it in a classical computer. One of the key differences is the no cloning theorem. You cannot clone quantum states, so you cannot copy data. And that means that doing nonlinear operations inside of a quantum computer is much more difficult than what you can do with classical computers. So, all of this is to say the heuristics that we have are kind of difficult to understand. We know of a lot of no-go average and worst-case performance theorems. And we've also tried to get rid out of those problems, And one of the interesting things is that you have vanishing gradients. Let's try to get rid of them. So we found a bunch of ways to get rid of those vanishing gradient problems. But it seems like quantum mechanics really doesn't want us to have fun. Because, for instance, let's say, and I'm going to get a little bit technical here for people. Let's say that what you're doing in a quantum computer is you're taking a quantum state rho, you're evolving it with a unitary, and then you're measuring some expectation value at the end of the circuit. This is what your loss function is going to be based on. Well, this is just the Hilbert-Schmidt inner product between this vector right here and this vector right here. If this is an n-qubit state, this is a vector of length 4 to the n. So your loss function is just given, the conclusion of this is take a very large vector, take another very large vector, and all that we can do is compare them. And this is how we extract information from quantum computers. This is pretty much all that we can do. So most of the loss functions out there are given from the inner product, a similarity measure between two very, very large vectors. And of course, the problem is that you can think about it even just intuitively, that if I give you two very large vectors in very large vector spaces, their expected overlap is bound to be exponentially small under very general circumstances. So whenever I go in my quantum computer, I try to align these two vectors somehow by just changing this with parameters. It's going to be very hard because when I measure, I don't get any signal. So what we have is that quantum computers suffer from a curse of dimensionality. The very same thing that we wanted to use a quantum computer to solve data, which is that they explore very large spaces, which much more efficiently than classical computers, is actually the thing that makes them very bad at just processing data. Because processing data is just manipulating vectors in high dimensional spaces. Well, because of how we need to extract information from them, this is a problem. And how do you solve this problem, the problem of concentration or the curse of dimensionality, is you can only restrict the subspace in which you're searching. You can put some bias in your model so that instead of living in a very large vector space, it lives in a smaller vector space. But then linear algebra comes and, everything that you're hoping for is just going to get destroyed by linear algebra, because linear algebra is going to tell you, well, all that you can do is explore exponentially large spaces or very small polynomially large spaces. There is no in between. And we can prove that there's gaps where you cannot do anything in between. So if you want to avoid all of these issues from the course of dimensionality, now you live in a very small subspace. And now because you're living in a very small subspace, you're classically simulable. So that was a very big detour just to say, quantum machine learning has the problem that it's operating in a very uncontrolled way in exponentially large vector spaces. And the only way to get rid of that is go to very small vector spaces. And if you're in a very small vector spaces, then you can have classical simulability. Of course, people might come back and say, well, we operate quantum states in exponentially large spaces all the time. Shor's algorithm is doing that. Grover's algorithm is also doing that. Well, the thing is that in the textbook algorithms that we have, the way in which we manipulate vectors is not random. We're not just fine-tuning the evolution times willy-nilly. Every single gate, every single operation that you're putting in a circuit serves a very specific purpose. And there's a computer scientist, Scott Aronson from University of Texas, who says something that I really like, which is that in a quantum computer, you need to manipulate the patterns of constructive and destructive interference, and you need to choreograph them very, very carefully to get something out of a quantum computer. That is absolutely not what we're doing here. We're like sending states out into the wild, and we might attend some tricks to try to manipulate them better, but at the end of the day, we don't know if this is going to work or not. So what is my current mindset regarding quantum machine learning? And please take this slide with just a ginormous grain of salt, because this is just my personal opinion, and it should not reflect what I think the majority of the field is doing. So the first thing that I'm going to say is that we cannot prove that these methods are going to work. We can only do heuristics. And maybe we can do really good heuristics, and we can find that quantum machine learning can give us some small marginal advantage, maybe order 1, in some fringe case where you found a good way to manipulate your state. You put a lot of biases into your model, and then you can manipulate your state, and you can get, say, like half of the time in a quantum computer that you would do in a classical computer. This is perfect. We're all going to be absolutely happy about that. Industry is going to be very happy if you manage to do that. So, I'm not going to say quantum machine learning doesn't work. It might work, only the Sith talking absolutes, but I don't know if it's going to work or if it's not going to work. I try to prove stuff. This is pretty much what I like doing. So for me, this is one of the big concerns that I have. But of course, the problem is that I have become a little bit cynical with this technology. And I think that as a community, we need to do a little bit better with how we're dealing with quantum machine learning. You see someone train a model on 4 qubits, it works, you put a paper out there. Well, how do you know if it's going to keep working once you go up the scale in more qubits, right? And we need to show that this is going to scale up. We need to do some really good comparison against classical machine learning models. Don't ask me how to do that. I don't know. This is what we've been discussing with Mikkel. It's a very hard question. And of course, the other problem is that there's papers that have taken the literature, Nature papers that have thousands of citations, and they've tried to reproduce the heuristics. You take exactly the same data set, exactly the same model, and it just doesn't work. And the reason why is because, that paper does not report the 3 months of parameter hypertuning that a grad student was doing just to get that quantum learning model to work. And, so does the quantum computer run in, some milliseconds or 3 months plus some milliseconds? So it's really hard to do like benchmarking out there. And I think that for me, my biggest concern is that there is a lot of positive bias out there. We want to publish good results. And as as someone that works with students, does mentoring, one of the biggest problems that I have with this is that I'm not really sure that quantum machine learning just willy-nilly is a transferable skill. What does that mean? You know, if I have a student and I teach them classical machine learning, they're going to be able to use those skills, go to industry tomorrow, and the same skills are going to be useful for a different tool, and this is all good. But I think there's a subset of the community that is just running variational algorithms, running quantum machine learning models, trying to see what happens. And I'm not really sure that that's a valuable skill that people will have in the future. And again, I'm not saying don't do quantum machine learning. I started doing variational quantum algorithms. I've been training circuits for the past 7 years now. And for me, what's been very useful is that in trying to ask questions of why do they work, why do they not work, I've learned a lot of quantum information, representation theory, group theory. So, you know, it's about like pushing past that initial stage. So if anyone here is doing quantum machine learning, I'm not saying, oh, you know, don't do this. I'm just saying try to push past that initial state and try to really understand what your model is doing, because then is where the hard and interesting questions are going to appear. Okay, so, you know, that was the big overview of quantum machine learning. Now the question is, how do we actually try to do quantum machine learning? What is our path forwards? You know, I don't want to just go out there telling people, don't do this, and just end it at that. So what I think that we can try to learn is learn from the history of quantum machine learning. And we can ask the question, how have we been creating quantum models? And I think that there's two main approaches that have been taken by the community. The first one is taking the quantum algorithms that we know and love, like Shor's algorithm or the HHL algorithm, and use them for quantum machine learning. So the best and brightest quantum, use them for data processing. That really didn't work. Most of these were dequantized. So then what we tried doing was taking the best classical algorithms like deep neural networks, you know, machine learning with thousands of parameters. We don't know what's happening, but it works in classical, so let's try to do it in quantum. Well, this also has a lot of issues. So I think that the main concern that I have is that we're rushing. We want to get to the end goal so fast that we're rushing. We're trying to just like use the best that we have in each separate world, but there's no reason why that should work. Why should a quantum algorithm work for classical data analysis? If you think about it, there's not really a good reason. And Shor's algorithm, why does it work? Why can we actually factor numbers in a quantum computer? I'm going to quote Scott Aronson again, and he says that there is a law of conservation of weirdness. If you want to have a very big speed up in a quantum computer, it has to be a very weird problem. And factoring actually turns out to be a really weird mathematically contrived problem. And it has a lot of structure in it, and that mathematical structure, quantum computers can exploit. So we can expect maybe this big exponential advantage. So maybe there's something to be done here. Maybe we can still try to find some classical problems that have this weird contrived mathematical structure that we can solve on a quantum computer. But general data analysis, it's really hard for me to see the motivation why a quantum computer should work at all. So again, I think that yes, there's a lot of work that we need to do here. Maybe we can exploit this sort of like underlying group theoretical structure, kind of like quantum algorithms do with hidden subgroup problem. This is pretty much, if you want to know why quantum computers work, I would say take a few time to read about group and representation theory, and then just read the hidden subgroup problem. That is why quantum computers work. It's just like very contrived mathematical problems, and I really like this. I think this represents at least the classical data analysis part. Simulation is a slightly different beast, but I really like this approach to quantum computing. So what we propose doing is we want to go back to the drawing board, and we want to try to do quantum machine learning, and we want to follow just two basic rules. The first is that we want to deal with quantum data. We'll discuss what that means, just because I don't know in which cases quantum computers should be good for classical data. So if your data lives in a quantum computer to begin with, then this is great, because if that data was the output of a process, a quantum mechanical process, some quantum evolution, and that we know that we cannot simulate classically, then we're at a good starting point, right? Because then maybe it's going to be harder to find a classical algorithm that does what we do. And then we want our models to be very simple and very interpretable. So went back to the machine learning books, started reading theory of computational learning and how do classical computers work, just to try to find where all like the simple snippets of like algorithms that actually work and are interpretable. And one of the nicest results in classical machine learning is this idea that, very deep neural networks are going to form Gaussian processes. So let me give you a primer on how artificial neural networks work. So if you've never seen a classical neural network or ever worked with them, but you understand this, I think you're going to be like 60% of the way there. Imagine that we have some real value data point x, and we just want to find a function that transforms it into another real value data point y. So what you're going to do, and this is what a neuron is, what a neuron does is it takes your classical data, it multiplies by a weight, it adds a bias, these guys are going to be trainable, and then you put some form of nonlinear function in here. I chose sigmoid. You don't have to choose sigmoid. You can just do different choices of functions here. This is all heuristics and rule of thumbs. And I can do the same thing here. I can take this x, I can send it through f2. So the output of this is a real number, the output of this is a real number, and then I can send these two to an f3, which takes two real numbers as input. So I'm just gonna take the first output of f1, multiply by another weight, the output of f2, multiply by another weight, and get a bias. And I just train these guys to solve a learning task. And this is neural networks in a nutshell. And what's really fun about this is that these guys right here, you don't really see their outputs. These are called like hidden neurons. And this paper, what it's going to tell you is what happens if I have a neural network that has a bunch of hidden neurons. I just have like a ginormous amount of them. We can just make them go to infinity. Well, the output is going to look like this. And then if you take your model and you randomly initialize the weights and the biases, you're going to see that the central limit theorem is going to kick in, and this thing right here is going to be normally distributed. So intuitively, what we can think about that this is happening is that there is a lot of tiny and independent noise signals that are coming from those weights, but the only thing that is going to survive is this overall correlation structure. So every higher order bump or skew gets ironed out. So this was a nice connection between neural networks and Gaussian processes. This, I think, in a way, is a theoretical result. People don't really use this for training. You can try to use this for doing some Gaussian process regression, but at the basic level, it's a fundamental connection between parametric learning and non-parametric Bayesian learning. So it establishes a nice bridge between those two. So the question is, how can we actually use this idea of learning? What if I have a stochastic process, and let me try to define what a stochastic process is. So let's just take this f, and I'm going to call it a stochastic process. And what it is a collection of random variables that are labeled by the points in an index set S. That sounds very abstract, but let's consider a specific case. Let's take S to just be a subset of the real numbers. And let's call each one of those things inside of S as the time. So, let's just say that S goes between 0 and 10. So what this is telling us is that f of x, whenever I take it, is just a random outcome. And this collection right here is just telling me how the randomness unfolds as I evolve through time. So for different times x's, I have f of x as a random variable. And we're going to say that f is a Gaussian process. So here I'm going to assume that S is more than one-dimensional. It might be a subset of Rk. And I'm going to say that this forms a Gaussian process if the distribution of this f is normal. So I'm going to have a norm vector and some covariance matrix. And what's cool about this is that we can use Gaussian regression for learning. Because what we can do is, let's assume that we have a model where our mean is just 0. And the entries of this matrix right here, or the kernel, I'm just going to call them k of xi, xj. So what this is telling me is that at any point, I can just assume that this is going to be normally distributed. So at time t, I can assume that this function is going to be a Gaussian distribution around 0 and with some mean. So this could be some measurable property at time t, and I just know that if I go and I probe it, it's going to be distributed around 0 as a Gaussian with variance sigma squared given by this kernel matrix right here. But what's very nice about Bayesian inference is that now I can use observations to update my prior information. So what I can do is that if you give me m observations, where you tell me what is the value of f of x at m points, and I call this a vector x, I can try to ask the question, what is the probability of this new point, which I haven't seen before, given these observations? This is a conditional probability, and because this is Gaussian, as we have by assumption, this is Gaussian, as we have from this set right here, we know how to compute this exactly, and it's also going to be Gaussian. It's going to be a Gaussian with a prior mean and a prior variance, so we just update our mean in this way, and we update our variance in this way. And what's really nice is that you can see that our original variance was sigma I squared, and now we're subtracting something. This is a positive number, so our uncertainty has reduced because of observations. In practice, how does this look? At time t, this is just x, and this is 0. If you don't give me any data and you ask me, what is the value of this function at time 2, I would just put a point here at 0 and draw a Gaussian around it. So it would just kind of look like this. But then what I can do is say, okay, but you give me this observation, this, and this, and now I can update this variance. It's still going to be a Gaussian, and what I'm drawing here is a 95% confidence interval. So the mean plus minus 2 sigmas, right? So what we can do here, and you see that as I approach the observations, my uncertainty goes away as it should. So if you have a stochastic process that forms a random Gaussian, that is normally distributed, we can actually use this for learning. And this is what people actually do, and there are many advantages of using Gaussian process for learning. The first is that it's interpolation by similarity. We don't have parameters, we don't have to train anything. The kernel is just telling us how similar our points are, and we can use this to mix and compare observations. Again, this is not parametric. We don't have to go and train parameters like we do in neural networks, and it also gives us uncertainty quantification. We have this blue area that tells me with 95% confidence, I think that this is what the outcome should be. Of course, there's some disadvantages, and when people use Gaussian process regression in classical machine learning, you don't have a proof that this is Gaussian process. So for instance, how do people use this in classical machine learning? You want to buy a house. So you can draw a plot right here, which is like square footage, and the y-axis is price. So what you can say is, okay, what is the price per square footage? I can just say, well, it's going to be some mean with some distribution, but then I can also just go and check what is the latest prices of the houses that have been sold. And then I can try to propose some kernel and try to use Gaussian process regression. Of course, no one guarantees that houses are actually Gaussian distributed. We assume that some poor sucker is going to pay a lot of money, someone really got a great deal, and maybe this is Gaussian, but it needs not be. So one of the big disadvantages in using classical kernels, Gaussian process in classical machine learning, is that you don't know if you actually have a Gaussian process. So the thing about this is that you might actually be using the wrong tool for the wrong task. You might use Gaussian process regression for predicting prices of houses, but if you don't know that this is an actual Gaussian process, this is as good as any other model that you can use, and that uncertainty quantification might not be useful. So what we want to do now is we want to show that we can actually find genuine quantum Gaussian processes. And this is what we did in this paper right here. We don't want to just slap Gaussian process into quantum machine learning. Again, we don't want to use the wrong tool for the wrong task. What we want to do is we want to find some quantum stochastic processes that will form Gaussian processes, and then determine if there's any useful tasks that we can solve with them. And again, we want to show and we want to try to see if there's any advantage over other learning algorithm. So I'm going to get a little bit technical here for just a second, but I'm also going to try to go a little bit quick because I don't want to spend too much time boggling down in details. What we're going to consider is that we have some ensemble of unitaries or more general channels. And we're going to consider again this familiar function, which is I'm going to take some initial state that is fixed, or that I can parameterize with some time t, and I'm going to send it by some unitary u that I'm sampling from this ensemble epsilon. And then I'm going to measure some expectation value O. Well, we can note that this is a stochastic process because I know that I sampled u from this ensemble, but I don't know exactly which U was sampled. So this gives me some uncertainty, you know, and it's only through observations that I can try to solve this task. So the first thing that we want to try to see is try to see if this is a Gaussian process. So our first attempt was, can we use the central limit theorem and then we're done? Well, it turns out that if you just expand this into the matrix entries of U, rho, U dagger, and O, the central limit theorem is not going to kick in because the entries of a unitary are small but non-zero correlated. And when you read the central limit theorem and you see like the IID assumption identically and independently distributed, that is extremely important. If you break that, the central limit theorem is going to break down. So we couldn't just show that this thing right here is going to be a Gaussian process just by central limit theorem coming and saving us. So what we needed to do was, okay, we have some random variable. We can try to take a collection of these observables, and we want to try to show that this is a Gaussian distribution. So if you have a random variable and you want to try to identify its distribution, something that you can do is just compute all of its moments. You can compute all the first order expectation values, all the second order expectation values, all the kth order expectation values. You need to compute infinitely many of them, and that might characterize your distribution. If you give me a distribution and you give me its moments, it's not true that the moments uniquely define a distribution unless some mathematical conditions are satisfied. So then we also needed to show that those conditions are satisfied. So we're just like brute forcing this, the worst possible case. You know, what we did at the end of the day is compute these kind of things right here. Again, I'm not going to get into too much details. If you know some group theory, what we had to compute, if E is just the Haar measure over a group, we can do some Weingarten calculus to try to do this. But of course, we have these entries that we need to compute for all orders for the commutant. Again, sorry about, I'm not going to get into the details at all about this. This is not the point. We had to develop some tools like asymptotic Weingarten calculus formula to be able to prove this. So we had to show how the commutant of certain groups behave. But more importantly, we can then compute some conditions on what these expectations are going to look like. And long story short, we can prove that these things right here are actually going to be quantum Gaussian processes. So we can find general conditions on what is the set of unitaries that I'm sampling the unitary from, and general conditions on what are the states that I'm taking from this sort of like time-dependent data set, so that we get what we like to call like bona fide Gaussian processes. And now we have quantum systems where really we take states, we send them through some unitary, we measure, and this is going to be, it's going to follow a multivariate Gaussian distribution. So I went very fast, so I think there's a few questions that I want to answer about this. So the first question that people might ask, if you know about Haar random unitaries, is I mentioned Haar random unitaries. You might ask the question, does U have to be an actual Haar random unitary? Is this thing that I want to try to learn actually Haar random? Well, the question is no, because this is just my prior. I just don't know that U was sampled from the group as per the Haar measure. So that means that whatever U I use, as long as it belongs to one of the groups that we've considered, our prior is it was sampled with the same distribution, so uniform. It has the same probability of being sampled as any other unitary. This is the completely uninformed prior, but U can be whatever you want it to be. It can even be the identity, if you so wish. So do we need exponentially large systems for this? Because we were talking about some asymptotics. Well, it depends. We can show that the convergence depends on this set, and we can get some corrections to terms that are going to vanish polynomially or exponentially. But in both cases, we can numerically show that Gaussian process regression is going to work. Then, you know, the title of the paper reads, if you remember, deep quantum neural networks converge, form Gaussian processes. So you might be saying, well, you've been trashing quantum neural networks for the longest time. Are you still going to have some unitary that is parametrized? Well, no. We call this quantum neural networks in the title because that's how the classical paper was called, and it was pure marketing purposes. Again, all that we have is just some unitary and some ensemble. You don't need to parameterize this. You can forget about all the things that I've been mentioning about parametrized circuits. And the question, more important question, is this useful? I don't know. But this is what we're trying to figure out. But at least we have the starting point where we have like provable bona fide Gaussian processes. So just let me quickly, to start wrapping up, give you a task that I think could be of general interest for quantum computing that we can try to tackle with this framework. So imagine that you have a quantum computer, and I'm going to work in this setting where you have access to the quantum computer for a limited number of time. During that time, you can make measurements, you can do whatever you want, and once this initial data acquisition phase is over, you no longer have access to the quantum computer, and you can only use the classical computer. And what we want to do is we're going to take, again, this set of quantum channels. I'm going to give you a probability distribution over those quantum channels, and I'm going to assume that I sample C. This was the unitary that we had before, but we've also generalized Gaussian processes to channels and not just unitaries. And then you have some parametrized states that are parameterized by some time parameter T. This is our data set over which we're trying to train. Remember, this is the prices of the houses in the y-axis. And the whole point is that you're going to get access to this channel C only the initial data acquisition phase. And this is very reminiscent to process tomography in a quantum computer. You have limited time access to some process, which you're going to try to learn. And once this initial data phase is over, what you need to do is I'm going to give you a new state, and you need to be able to predict what is the expectation value of sampling a new state here, sending it through the channel to which you no longer have access to, and measuring some properties. So again, this is why we find this sort of functions. So how can we solve this if we don't use Gaussian processes? You can always just try to do process tomography, learn the whole channel. The problem is that this is very expensive, and this uses no information about what the ensemble is, the probability, the set of initial states, not the measurement operator. If you have some knowledge, for instance, E is an ensemble of unitaries, you can try to do Hamiltonian learning. I'm just name dropping here. I'm sorry if these things don't mean too much. I just want to compare against other methods. But of course, this also doesn't use information about those three. Or what we propose, and this is why we think this could be useful for characterizing quantum computers, is that you can use our Gaussian process regression. You can just do Bayesian inference. Because now we think about this as some random variable, and given this ensemble, we can compute the distribution and know under which cases is going to be a Gaussian process. So, you know, I think I don't want to go into all of these details. But again, it's this idea of updating prior with observation. What I want to try to end up with is some examples where this actually, I want to try to convince you that this works. So the worst case scenario possible is that you tell me it is a unitary from the unitary group acting on your Hilbert space. This is the worst prior that you can have. This is what the kernel should be. But what's fun is that we can actually try to do some learning. This is on 25 qubits. These are my training points. And you can see that we can try to do some interpolation and also some extrapolation, where of course uncertainty is going to blow up the more I go away. We can also try to extend this if we only care about predicting local observables. We can do some tricks. This right here is 250 qubits, where we've used some simulation tricks to be able to scale this up. But again, you can see that this one I really like, because, you know, I can just measure on this dip, I can just measure on this dip, and somehow I can predict that over time this is going to happen. So this is a lot of fun. Also, we can try to predict some other stuff over other groups, like free fermionic evolutions. Can I play this? Let me see if I can hit play here. I just want to show you how the Gaussian process gets updated. Is this running? It's not running. How do I make it run over here? Oh, there it is. Perfect. So what I'm doing here is, first I had my 0 prior. I put one training point as an X. You can see how my prediction gets updated. And as I put more training data, you can see that my prediction is going to get a little bit better and a little bit better and a little bit better, until eventually I have something that pretty closely matches the evolution over time. And eventually, if I have enough data points, here you can see that this is just 7 training points. I believe that this is 18 qubits, so I'm just measuring 7 training points. And eventually, you're just going to get kind of like perfect learning whenever your Gaussian process is just capturing all information. And if you do Gaussian process, then you can also do Gaussian optimization. So now you can think about rho as being somehow parametrized, and you're trying to optimize it. So we're thinking about this channel U that I'm trying to learn for metrology is just some interaction that I have some information for. And now I'm trying to find a state that is as sensible as possible to this interaction. So I need to change the state to maximize the amount of information that we can do. So here what we're doing is we're just parametrizing our initial state by 2 parameters, T1 and T2, and we're trying to find the global minima of this very horrendous function. You can try some random initialization and use gradient descent, LBFGSB, or Kobila, or gradient-free methods, kind of like Nelder-Mean. And whenever you initialize, you can see that all of these just kind of get stuck in local minima around here. But Bayesian optimization, the power is active learning, and this is a non-local optimizer, and you can see that this is just telling me which are the points that I should sample. And after 7 optimizations, I can find the actual global minima of this function right here. So for at least quantum sensing applications, this is really nice. And we can actually see that what we're doing is maximizing the change, the gradient of my function over time. This is just a cut here. And this is what you would do with the quantum Fisher information. You're just making your state as sensible as possible to the thing that you're trying to measure. So things are working like they should work. Of course, you can ask the question, well, eventually, if you give Gaussian processes enough resources, it's going to catch up with Hamiltonian learning or process tomography. And this is what we see. And we can just compare here. This is learning a unitary using very fancy Hamiltonian learning tools. This is how many training points I have and what is my total shot budget for training. And you can see that, of course, if I have a bunch of training points and I have a ginormous amount of shot budget, Gaussian processes just does the same as Hamiltonian learning, as it should. We can prove that they're asymptotically equivalent. But the interesting thing is the imperfect learning case, where you don't have enough resources for Hamiltonian learning to really shine. Because in Hamiltonian learning, you're dividing your resources kind of like you don't have a prior. You're just trying to divide them the best that you can. Here, we use active learning. And then Gaussian process tells us this is the state that you should pick to get the most information. So this is whenever you have a limited amount of training data, we can actually expect our methods to be better. With that, I just want to wrap up and say that what we wanted to do is, yeah, we can show that some things are Gaussian processes. We can do Gaussian process regression. We don't know if there's an advantage. This is still open research, but I'm very excited about this. So my outlook is, I think that we have to go back to the drawing board. I don't know what the other methods are doing. Maybe some of them, their futures look bleak, like parametrized quantum circuit. And of course, don't take this as quantum Gaussian processes is the way to go. Again, only the Cth talk in absolute. And I don't know if Gaussian processes are going to be better than some other stuff. But at least I'm very happy that we can do something different. And maybe we can get some polynomial speed up when we have quantum data and we have this imperfect learning. And what I really like about this is that because we've proved that those are bona fide Gaussian processes, this is the holy grail of Bayesian learning. We have the right prior. So we have the right tool for the right task. And it seems to be a fairly important task for quantum computing, which is just like characterizing what the device is actually doing. And again, I'm a little bit cautiously optimistic, is what I would call about this. So with that, I want to thank you. And I just want to take this opportunity to say that LANL, we hold a quantum computing summer school every year. This is aimed at undergrad and graduate students. If you have some experience in quantum, this is 10 weeks where you're going to do research paired with LANL scientists. We've had the pleasure of hosting 2 students. I think they're both in the room right here. We're wearing actually the matching T-shirts for this year, which I think you guys designed. so I'm really happy about that. And I encourage you to apply. Applications are going to be open in December. And I thank you for your time.
So, questions?
Hello. I have a question about, it's one of the history slides. I think it's the good.
Yep. Let me try to go back to it in a way that I don't have to Okay. Is this changing? It's not changing.
It's not changing.
Let me go back here and try to reshare. Yep. There you go.
No, that's not it then. There was one that I think it's with the VQAs that have the graph. Because I had a question about that graph.
Yes. This one. It's before the good. Yes. Sorry about that. Okay, here we are.
Yeah. Is that time, is the time axis like going to the future? Or no?
No, this is just the number of papers per year, so...
No, yeah, because over there is that 2025, and that would be, what, 2026?
Yeah, 2026, there's 0 papers just yet.
Yeah, I just want to know, is that a prediction, or is that just because it...
No, this is taken from Scopus. So this is just like index papers working on quantum machine learning. This is actual data.
No, but we don't have data for 2026.
And that's why we don't show data for 2026. This is the 2025 point, and 2026, this is 2027. It's going in increments of 2 years. Yeah, sorry, this is very small. But yeah, this is why 2026 is 0. 2027, we also don't have any data.
Okay.
Yeah, I'm not making this up.
No, I was just wondering. Yeah, I don't know if this is like a second question. When you're talking about stochastic quantum processes, do you think this involves like random circuit sampling experiments? Could that be characterized by the...
So the tools that we developed can be used for random circuits because there you're actually sampling random unitaries. So what we can use is that we are characterizing what is the output distribution of random circuits. And then you can do like concentration properties. So for instance, there's concentration of measure properties where you use what is the probability of deviating from the mean. We can use R bounds, and you can get slightly improved bounds on concentration for random circuit sampling experiments. So this we discuss in the paper. We improve the bounds on probability of deviations. But for Gaussian process, we don't actually do that because there you have, yeah, so the short answer is yes, that is a stochastic process because you sample the random unitary and then you're just getting bit strings out of it. But that's not what we're considering, because in our case, U is not random. This U that we're learning is some physical evolution that the system is undergoing. So in sensing, that U is whatever is encoding the parameter into your quantum system. So it's supposed to be something interesting and physical and not a random circuit.
Okay, thank you.
I have one question. When you take the Gaussian processes from the classical literature,
yeah,
is something that was done and now the quantum machine learning like go in other direction, or is something that is currently used in the classical framework?
I would say nowadays it's one of those things that you read in textbooks. People still use them, but I think you can get much more advanced methods for regression. I think the main problem that they had is that you didn't really have a good kernel. People just propose kernels. So most kernels are just like similarity measures. Like you have the pricing, of houses for square footage. You just like subtract that square footage, you put it in an exponential, and then your kernel is like e to the minus like square footage 1 minus square footage 2 squared over some trainable parameter. So I think that the problem that they had is that because you don't know if it's a Gaussian process, the predictions are just kind of like whatever. And now people are doing this with much more advanced methods. So I would say that this is not what people are doing in classical machine learning. I'm also not an expert. If someone here actually uses Gaussian processes in classical ML, I'd be interested in hearing it. But from what I've read, this is kind of like old, boring stuff. But again, this is what we want. We want the old, boring stuff.
Thanks.
Thanks for the talk. So my question is, you somehow gave up with processing classical data using quantum machine learning, but is there any chance that you take classical data, process with a quantum algorithm, and then you try to infer some properties of the solution of the already processed state with these kind of techniques?
That is a fantastically great question. So one of the things that I swiped under the rug was that there is some conditions on the data set that need to be satisfied for you to actually have a Gaussian process. There's conditions on the distribution, the data set, and the measurement operator. If you take those conditions on the data set and you assume that those states come from data encoded, then I think that you can do the learning by, again, classically simulating the whole thing, because the conditions for which you get Gaussian processes actually lead to kind of like good classical simulation methods for your data. So yeah, there seems to be no good free lunch there. Maybe there's some fringe case, but again, like, man, it's just linear algebra, and linear algebra is just kind of like slapping us, saying like, you should not do this. It's kind of fascinating, and there's something deep there which I still don't see.
Thank
you. Thanks for the talk. Can you? It's not clear to me how this quantum Gaussian process method that you explained can be really related to Hamiltonian learning, probably because I'm not an expert. But what would be your random group of unitaries and so on?
Yeah, that is a great question. I think that the whole idea is that, again, you have some states from some training set, and you're trying to learn what the expectation values are going to look like after this U. So something that you could do is just learn this unitary, if you know that this is e to the minus iht. And the conditions on which is the Hamiltonian learning process to do is what that Hamiltonian is. Usually whenever you do Hamiltonian learning, say that it's a two-local Hamiltonian. You start with the assumption that it's a two-local Hamiltonian, and then you just learn the coefficients. So that is kind of like your prior there. But I can also tell you that Hamiltonian is a free fermionic evolution, and then you can use that for learning. So yeah, the information that we use to learn this U, Hamiltonian learning can also use it. And they both will allow you to do this prediction. And we've actually shown that our epsilon errors with probability 1 minus delta are asymptotically exactly the same as Hamiltonian learning. So we know that Gaussian process will not do better than Hamiltonian learning, because Hamiltonian learning is known to be optimal. So, but that is in the limit of a large of data. In the limit of small amounts of data is where we can expect some improvement.
So essentially you would evolve with different times at random, and then or
you would take different states. This U is fixed. This U doesn't change. You take different U's, and then you just measure. You get information from measurements, and you update your prior. And active learning tells you which states in your data set you should send. And this is where the magic comes in.
Okay, thank you.
I think you were raising a question for a while.
Yeah, we have time for the last question.
No, but we're also chatting later, so we can also chat more. So, no, please go ahead.
Okay. In this very same slide, when you use these Gaussian processes, these Bayesian processes, what you usually want is to learn U, and you have access to different initial states, and you know what your observable is.
Yes.
Could you try to use this setup for VQEs and try to make them work?
So the thing is that, what are you trying to learn there? And I think that, again, the problem is going to be that if these states, because here the only thing that is parametrized are these states right here, right? So the problem is that if these states are coming from like a randomly initialized VQE at different times t or at different parameters, then you are going to fall in this condition right here. So two states that I obtained from randomly initializing my circuit, sending one state, another random initialization, sending my state, I can expect these guys to be roughly order 1 over d, their overlap. And this is actually the overlap of 2 hard random states. Give me 2 hard random states, their overlap is going to be 1 over d. And whenever that happens, your correlation is 0, and Gaussian processes doesn't work. So again, like linear algebra is just telling us something. So we actually thought about that, but you really fall in this case because you're falling into like concentration of measure problems again.
Well, first of all, thanks a lot for being skeptical enough, which is something that is not very, that doesn't often happen. I have a couple of questions. One thing is, correct me if I'm overstating what you said, but to some extent you said that quantum computing is all about the hidden subgroup problem.
For data analysis, for simulation, no. Simulation has.
Okay, because that's exactly what I was. Yeah, sorry. Yeah, okay, done. Then, for the very general things, then you said that QML would be great for teaching quantum. I can tell you, I'm always thinking if I were to teach fourth year quantum mechanics again, I'm always thinking, well, I always think I have to put in some quantum information.
Yeah.
But I would have never thought to put quantum machine learning there. So what is it that you mean?
So what I meant was, and I usually make this disclaimer because I know that I can be a little bit too aggressive on quantum machine learning, and then, if someone is working on quantum machine learning, I don't want them to feel like, oh, this work is maybe not what they should be doing. So what I always say is, if you're working quantum machine learning, and I think getting to work into quantum machine learning is a really nice way to learn quantum computing. I don't think I understood the subtleties of quantum computing and quantum info until I worked in variational algorithms. So for me, it was kind of like a gateway drug to like quantum research theory, representation theory. So this is kind of like what I tell people is like push past just like training and go into like deeper concepts. But I think it's a really good point to start learning variational quantum computing. Just like it's very natural. You use Schrodinger equation to parametrize unitaries, and then you get measurements from information. So it's a nice way to learn quantum mechanics.
And yeah, there was one last which has to do with all the references you made to Scott Aronson's sentences or what have you. Yeah, but that brings me to in quantum computing. I mean, this what Aronson is saying, it can be rephrased in the form that quantum computing is good if you manage to have a global question that cannot be answered locally, classically, or that you need to look at all the local possibilities, and you are kind of globally. You're moving it to your global question by interference is giving you something. So aren't there any guides as to that also for machine learning, that interference is the nuclear thing? And this is it, because it's going to hit me otherwise.
No, that's a great question. I think it's the right way of thinking. I don't have an answer. But for instance, when I said that there's some approaches to QML which I'm not touching, which are very interesting, the question is, what is the quantum phenomena that you're doing? Scott Aronson talks about interference, constructive and destructive. There's other quantum machine learning models that use quantum contextuality, for instance. And that is a purely quantum phenomena. And they can show that you can use quantum contextuality for some learning tasks in, say, like language processing, natural language processing, where context is everything. So the interesting thing about that paper is that they ultimately find out that maybe it's just a small polynomial improvement, so kind of like order Grover again, but it's based on quantum contextuality. So you can understand it from like first principles. So maybe that's kind of like what I was trying to hint at, like, yeah. Thank you.